An algorithm has big O n complexity if it eventually always performs less than or equal to a constant times n number of operations. To clarify this definition, I have plotted the number of operations performed by 3 algorithms. The first one always performs fewer than n operations, which is this green dotted line. Therefore, it is a big O n algorithm. The second algorithm has this area at the beginning when it performs more than n operations. This is quite common in practice because we have to define and initialize variables before we do the actual work. But notice that there is this inflection point after which the algorithm performs fewer than n operations. Because it eventually always performs fewer than n operations, we say that this algorithm is also big O n. The final algorithm performs more than n operations. Should we then say that it is not a big O n algorithm? No, we shouldn't, because there is this inflection point after which the algorithm always performs fewer than 2 times n operations. 2 is a constant factor, independent of the input size. For this reason, we conclude that the third algorithm is also big O n. As long as we can find this linear function, const times n, which provides an upper bound for the number of operations executed by our program, we can say that it has a big O n complexity. Because of this linear upper bound, big O n is also known as linear complexity. Next, we'll look at a few examples of big O n complexity that you might encounter in practice. Let's say you want to iterate through an array using a for loop. Your journey through the array will look something like this. Because we are visiting each node once, we are performing roughly n operations, which is smaller or equal to const times n when const is 1. So we can conclude that this for loop has a big O n complexity. Let's now look at another for loop, this time one that jumps c steps at a time, where c is a constant number independent of n. The number of operations performed is n over c, which is smaller or equal to n. So once again we conclude that this for loop also has a linear complexity. What about the 2 loops combined? Well, the number of operations performed is roughly n plus n over c, which is smaller or equal to 2 times n. This fits with the big O n definition, so the complexity of the 2 for loops combined is big O n as well. As a conclusion, iterating to the input values a fixed number of times takes linear time. Besides for loops, we can use while loops and recursion to iterate through input values. But be careful with recursion, it's a more advanced topic, and if you're not careful, instead of big O n complexity, you might end up with a much worse runtime. Comparing 2 strings takes at most n operations because we have to compare each individual character. In theory, the worst case complexity is big O n, although in practice many compilers and interpreters use a variety of optimizations to improve the average time complexity. Let's say you have an array of size n and you want to add an extra element at the end. What is the complexity of this operation? Keeping in mind that the length of the array is fixed when the array is defined, we actually have to create a new array, copy over all the values, then add the new element. For this reason, the complexity is big O n. Imagine now that you have to sum up n values. Whether you store those values as an array or a linked list, the complexity will be exactly the same, big O n. In practice, however, summing over an array is faster, because of the way memory is allocated and accessed on standard hardware. So far we've talked a lot about time complexity, but the big O notation can be used to measure all sorts of mathematical equations, including the amount of memory used by a program or the number of input-output operations performed. In this example, we look at the adjacency list of a graph. The principle is simple. For every node in your graph, store a list of all the neighboring nodes. The amount of space used is linear in the number of nodes and edges, so we can say that the adjacency list uses big O v plus e space, where v is the number of nodes and e is the number of edges. Here's all the information I have mentioned so far, all on one screen. Feel free to take a screenshot, share it on social media, or check out nextlevelup.io for more extensive articles on the big O complexity.